Okay, let's get started. Okay, so let's see. Okay, I will try to finish this quicker. It still will take maybe 1.5 hours at least, I think. I moved some of the modules to the homework part, so the lecture part can be a little bit shorter, but still it will be 1.5 hours. So last week we kept talking about return-oriented programming, and this week we are going to switch the gear a little bit. Technically, what we're talking about today is not really software security. It's probably still system security, but it's more related to the micro architecture part. That means it's beneath the instruction set level. It's actually inside the CPU. It's about cache. So we're going to talk about cache side channel attack, and I will give several concrete examples, several specific cache side channel attack method. Then we will talk about the very infamous Meltdown and the Spectral vulnerability, which has been a really big issue in the last 3-4 years, I guess. I don't know how many of you heard about this Meltdown and the Spectral before. So they are both related to the optimization inside of the CPU, and both of them somehow rely on cache side channel attack, but it's beyond cache side channel attack. Okay, so first we talk about cache side channel attack. Some background knowledge here. So in the last 40 years, the speed gap between the CPUs and our main memory is getting bigger and bigger. So the CPU, the frequency gets much higher, and the storage inside the CPU is made of static RAM. So static is much faster, made of 6 transistors, I believe. One SRAM cell is made of 6 transistors, so it's quite expensive. On the other hand, we have the main memory. Usually we use dynamic RAM, and for each dynamic RAM cell, it is made of one resistor and a capacitor. Okay, so it's much cheaper. However, the capacitor will always lose power. That's why they have to recharge it every, I don't know for how long. I'm not really in that area. So DRAM is much cheaper, but the speed, it's hard to make it faster. But the SRAM, also the CPU frequency, everything is getting faster. And the speed gap between them are getting bigger and bigger. Obviously, the ideal memory storage system should be super fast, as fast as the CPU, super large, and also super cheap. Unfortunately, in reality, we don't have such a memory and storage system. Fast storage systems usually are very expensive, like the SRAM inside of the CPU, and also small, because, like I said, SRAM cell is like 6 transistors, so it takes much bigger space than one DRAM cell. Very affordable, and the large storage systems are usually very slow. Now, DRAM, obviously, in the hierarchy is still considered a very fast one. We have hard disk, we have even optical storage, those are even slower. So the strategy is to handle this gap between CPU and DRAM is put something faster closer to the CPU, and also keep frequently use the data code in the faster storage. So we do not have to always search the data we want in the slower storage like the DRAM. Then CPU cache is such a faster storage because it's part of the CPU. It's made of very expensive SRAM. So it's as fast as the CPU, and it's much faster than the DRAM. So cache serves between the CPU and the main memory. It keeps a copy of the most frequently used data from the main memory in the cache. So when the CPU looks for some data, it doesn't have to talk to the main memory DRAM. It can directly get that from the cache, so much faster. And modern CPUs will always have multiple levels of caches integrated in the processor chip. For example, the Intel CPU, your laptop, your desktop usually have at least 3 layers, 4 layers. The phone system you are using usually 2 layers of cache. Sometimes have 3 layers. Some very low-end IoT devices, they do not have cache because it's too expensive. Okay, so here is some data I got from a paper, but this data could be a little bit outdated. So that's the average access time to accessing data, the speed in 2012. If the instruction access data from the cache, it take 0.5 to 2.5 nanoseconds. If it access the same data from main memory, the DRAM, it will take 50 to 70 nanoseconds. That's like 100 times slower. If you access flash, it will be even slower, or magnetic disk, your hard disk, it could be quite slow. Okay. So 2 important concepts here. One is called a cache hit, another one is called a cache miss. A cache hit occurs if the cache contains the data we're looking for. A cache miss occurs if the cache doesn't contain the requested data. So in that case, the CPU has to ask the data from the main memory. Obviously, cache hit is good because cache can get the data much faster than the main memory. If you have a cache miss, then it's kind of bad because the CPU has to wait longer for the data. The cache hierarchies, like I said, usually the CPU we are using right now has 3 or 4 layers. Layer 1 cache is closest to the CPU, and most of the CPUs we use right now, the L1 L1 cache is divided into code cache and data cache. So there is a cache area specifically for code. There is a cache area specifically for data. Usually our L2 or L3 cache are unified. Not only unified, sometimes they are also shared between different CPU cores. Okay, so this is a layout of a very old CPU. I'm not sure what this CPU is. I kind of believe it's a RISC CPU because you can see there's a node store. I think it is a RISC CPU. So as you can see here, what do we have? We have a floating point unit. We have the load store module. We have a data cache. Okay, so this is a level 1 cache, data cache. Then we have an instruction cache here. So this is also level 1 cache. Then we have an execution unit. We have a control unit. So this one actually have an MMU, memory control unit. However, you can see the largest area for a CPU is reserved for cache. So this is L2 cache. So this is on the same die, the same chip. More than 50% of the area is used for the L2 cache. If you consider the L1 cache, probably 65% of the area is actually used for cache. So those other computing modules are actually very small. This is another CPU. This is also actually old. This is 20 years ago. This is Intel Pentium 4 CPU, and you can see those 2 parts. Those are L2 cache, 256K, quite small. So modern CPU, I believe we have maybe 8 megabytes of cache, or even bigger. So you can say there is other cache area as well. Okay, I have another picture. So this is a quite modern one, probably 5-6 years old CPU. And this CPU has 8 cores. So this is an 8-core CPU. Those areas are for the IO. Those are the 4 8 cores. Then between them, among them, there is a shared L3 cache. So every core can access this L3 cache. And each core has its own L1 and L2 cache. And this is a memory control part. Okay. Another important concept is a cache line, or some literature call it cache block. So this is the minimum unit of information that can be either present or not present in a cache. So if you want to load something into cache, you do not load it byte by byte. In memory, you can do byte by byte, but for cache, you don't do byte by byte. You will load a cache line or cache block. So usually in Intel and ARM CPUs, that's 64 byte. So if you, in your code level, machine code, you are accessing 1 byte in the memory. The CPU, what actually it does, it will load 64 bytes of that continuous memory area to the cache. Then the CPU can retrieve from the cache. Okay, even if you're only using 1 byte. So the reason to do that, obviously, it will be much cheaper. If you, every time you want to load 1 byte, then the circuit level, it will be much more complicated. And you already see that cache is very complicated. So if you want to read only the 1 byte to cache, then the cost will be even higher. And all the cache we're using right now, no matter you are using Intel or ARM CPUs, the cache we're using is called N-way set associative cache, which means any given block or given line in the main memory, which means 64 bytes of continuous data in the memory, they can be cached in several places, not only one place in a cache. But how many places you can be cached to is determined by how many ways the CPU, the cache has. So usually that's called, here we call it N-way. So there are N different cache lines that data can go to. And those N different cache lines, we call it one cache set. So this is a little bit confusing. I will have more animations later so you can understand what's going on. Okay. So imagine we have a 32-bit machine. So every memory address can be represented into a 32-bit address, right? So we have been saying this a lot. But this address, those 32-bit address can be divided into 3 different regions. The least important regions, they are offset. So in this case, we have 6 bit in the offset. So 2 to the power of 6, that's 64, right? So 64. So those 6 bits can represent all 64 bytes in the memory. Then in the middle, this area is called a set or indexed. And the higher bits, they are called the tag. So if we have a 32 KB 4-way set associative cache, that matter is this is data cache or instruction cache, then each line is 64 bytes. So this is how we are going to divide it. Okay, first of all, there are 64 bytes per line, which means we need a 6-bit for the offset. Then the number of sets can be calculated as the cache size. In this case, 32 KB cache size divided by the number of ways. We have a 4-way cache. Okay, then each line is 64 bytes. So in this case, we have 128 sets in this cache. So a 32 KB 4-way cache has 128 sets. Okay, I have some animations here for you. Let's say we have some data, and that data has an address, right? We're talking about 64 bytes of continuous data. It has some address. This is its address. According to its address, we will know which set it goes to. So here are the set numbers. So it can go to, this is called a set. This set, since it's 4-way, this set has 4 lines. So the data can go to either of those 4 cache lines. Can be this green one, can be this green one, or here or here. However, that data cannot go to another set, okay, like this, because the set, which set it goes to is determined by its address. So it cannot go here. So what actually is stored in this cache is, first of all, there is a valid bit to tell if what we stored here is valid. Then we have the tag, which is this thing, which is 19 bits here. The reason we store it here is it's not stored anywhere else. Then obviously we have the data itself, which is 64 bytes. So when we look at this item in the cache, we will know what data it is, we know what tag it is, and we know the set number. So we can reconstruct its address from the tag and the set number, right? We cannot get the tag anywhere else. That's why we store it here. Also, there is a D bit, usually it's a dirty bit. It means whether what we have in the cache is the main memory is consistent. So when the CPU does some calculations, it may not push the result back to the main memory. The result may stay in the cache. In that case, the cache will be labeled as dirty, which means it's not consistent with the main memory. If there is another CPU try to read that address, then this CPU core has to push that data to the main memory, because the other CPU may not be able to directly access this core's cache. Does that make sense?
Yeah.
Okay, then let's keep moving. Obviously, cache is a much smaller storage than the main memory. Even though for one memory address, there are several places in the cache you can go, but obviously there are many more different addresses in the memory. They could go to the same cache set, right? For example, we have different tag here. The tag is 19-bit. That represents many different memory addresses, and they can all go to the same set. And all those addresses, if they map to the same cache set, those are called the congruent addresses. So those congruent addresses, the data in them, they compete for cache lines within the same set. And there are several different replacement policies to decide which lines to be replaced when new data is coming. So some popular algorithms, the first one is least recently used. So I think this one is implemented in most CPUs. So let's say we have 4 cache lines in this data set, the cache set. All of those, so this cache set is full. Then there is another data coming in, needs to store in this cache set. Then we need to decide which one we need to evict from the cache, then put the new data in. The least recently used one, where obviously evicted one has not been used for a while. And imagine everything is implemented at hardware. So at a hardware level, we have to record, we have to remember somehow which cache line was least recently used, right? Then there is a first in, first out algorithm. I don't believe anyone uses this algorithm. And also there could be least frequently used. This one sounds like very expensive because for each cache line, you need to remember how many times it has been used recently, right? So that means more circuit, more expensive. That's why some of the low-end CPUs, even the ARM CPUs, they're not that low-end, but they just use a random algorithm. Every time new data can get in, they randomly evict some data in the cache set. So it's easier to implement, which also means the cost is lower. So what is cache side channel attack? Cache side channel attack basically utilize the time differences between a cache hit and a cache miss to infer whether specific code or data has been accessed by the victim recently. I will use this animation as an example. So the code I'm showing here is actually ARM code, because my research area is actually using ARM. So all my examples are using ARM. So we have, let's just say we have two registers, R0 and R1. And R0 has a value 3000 in hex. That's an address. That points to our main memory. This is our main memory. And this is the address for each data. And this is a value of each memory address. So we have a load instruction using R0 as the memory location and load the value in memory to register R1. So you may think, especially what we are doing so far in the class, you may think what happens is when this instruction is executed, the data 1 is directly load into the register R0, right? But underlying, what really happens is much more complicated than this, okay? What really happens is between the register and the memory, we have this thing cache. When this instruction is executed, the CPU will first try to retrieve the data at the location 3000 hex from the cache. The CPU will ask the cache, do you have the data at this memory address? If the cache says, I have the data, then that data is directly loaded into the register super fast. If the cache doesn't have the data, then the cache will retrieve the data from the main memory, then give the data to the register. This is what happens. So if it has the data, usually it's super fast. Without that data, it will be much slower. And we will be able to measure the time difference as an attacker just at the instruction set level. So what we do is, if we measure the time between before executing this instruction and also after executing this instruction, then we subtract the time 1 from time 2, then we get how long this instruction takes. Then we will know if the data was actually retrieved from the cache or retrieved from memory. That's the basic idea. So built on top of that basic idea, we have many different attack primitives, and they all have kind of catchy names like evict time, prime probe, flash reload, evict reload. So we're not going to talk about all of them. I will give some examples on 2 of those approaches. So those approaches, even though those names are very catchy, doesn't really mean the attack take 2 steps. Sometimes the attack takes multiple steps. The first approach was proposed in 2005. There was several papers talking about using cache side channel attack to steal keys for AES crypto algorithm. So the eviction time, the idea is very simple. So this is the basic idea. First, there is a victim program, and there is a attacker program. The attacker program will measure the execution time of the victim program. Then it will evict a specific cache set. Okay, evicting a specific cache set is easy because you know the cache set number, then you just access some congruent addresses for that cache set, then you can evict whatever is already in this cache set. Then you measure the execution time of the victim program again. Okay, so if the time measured by step 1 and step 3 are the same, what does that mean? Any idea there? If the time you measured are the same. I see someone in the chat box. I'm not sure if
then they were both misses.
If they both misses, well, not necessarily. Yeah, you're right. So if they are the same, means it basically means the victim program didn't really access any memory location that will go to that specific cache set, right? Does that make sense?
Yeah. So it's not, so it is a miss because
yes,
it wasn't able to access. Okay.
Yes. So in that, that actually means that the victim program, because remember, the cache set somehow also maps to the program's address space, right? The memory address space. So using that, we can infer if the victim program has been accessing some data in its own memory space. And for crypto algorithms, those data for AES, that could be very sensitive, could be SBox. I think it's called SBox, yeah. Some SBox entries. And whether to access some SBox entries is determined by the crypto key. Then we can infer what was the crypto key. So that's a basic idea, yeah. Eviction time was an old approach. So I'm going to talk about some more advanced approach. The first one is called prime and probe. Prime obviously just means to get something prepared. So we have the attacker's address space here. We have the victim's program's address space here. And we assume we have a 4-way 128 set cache like this. The first step in prime and probe, the attacker will occupy a full set. Okay, this is easy just by keep accessing some congruent addresses. It will occupy a full set. Of course, everything in cache, there is no instructions to directly manipulate the cache. So to occupy this, the attacker can just read memories. So there is, it's not always 100% you can guarantee you occupy that. But if you keep doing this for quite some time, the chance you do not occupy a full set is also very low, right? So let's say attacker occupies this set. then the attacker will allow the victim program to run. The victim program will execute its own code, it will access its own data. Then it may access some data memory locations that is congruent to this memory set. So this cache set. So some cache lines in this cache set will be evicted and replaced by the victim's data, right? Then after that, the attacker access those memory again, and also measure the time. So this time, when the attacker access some of the memories, it will be very fast because those data are still in the cache. However, some of the memory locations, the access will be very slow because the data on that address is already evicted. Then attacker can infer what the victim has been accessing in its own address space. Okay, so that is the prime and the probe attack. Does that make sense?
Well, I'm sorry. So the program that is the attacker, how is it able to see, like, is it able to, are we assuming it's able to access like the dirty bit, or how is it able to see that?
It can, you can, there is no instruction to access those specific bits.
Yeah, because the operating system.
Yes. So what the attacker does is just something like this.
Oh, just checks the values at those spaces. Okay.
Not really check the value, just load the value. The value doesn't really matter. The value doesn't matter. What matters is how long does it take.
Oh, yeah.
Yes.
Sorry.
So the prime step, it does this, use different address. The measure step, it also use the same instruction, but it will measure the time. Yeah, that's
gotcha.
the only thing. Then obviously this approach is not very, let's say, accurate because everything we're doing at a cache set level. There is another more fine-grained approach is called a flush and reload. I think this one works on Intel and also this one we can do at the cache line level instead of cache set level. First, we'll assume a memory block is cached. Then in this case, the attacker will specifically flushes this memory block out of the cache. There are instructions to do that. Okay. After that, then it will read the victim may or may not access that block again. If it accesses that block, then that memory block will be brought back into the cache again, but not necessarily in the original way, right? You know that it will already be brought back to the same cache set. Okay. Then the third step, the attacker will try to access that block again, and this time measure the time. So it can say if the attacker, the victim actually accesses some memory. So this one is a little bit more specific and more accurate because we're talking about the size of one cache line here. Okay, the previous one could be bigger than that. So next, let's look at a very concrete example. This is a piece of code I wrote before based on some code I saw somewhere. We are going to use this code to measure the access time at my computer. Okay, so let's see what I have here. First, we have a global variable, which is array, and the global variable is huge. So 4096, that's one page in the Intel CPU. Then we have 10 pages. So this is a big global variable. Then in the main function, we have the junk. I don't remember what this is for. Let's revisit this one later. Then we have two local variables, time1 and time2. However, those two local variables, we do not store them in the stack. We directly store them in the register because I want to show you guys a very accurate thing. So those are in the register. Then we have a pointer to show to point to address. Then we have a counter here. So we first initialize the array, and we only initialize the first byte in this case. Okay, we have a huge array, 10 pages. We initialize the first byte of each page. Then, so what will this do? This will bring that first. The reason we use the first byte of 4 pages because they are not congruent addresses. Okay, so they are guaranteed to go to different cache set. Then we were, when we initialize this, we're doing a memory write. And I believe this will also bring the data in that memory address into the cache. So this one first guarantees that we reset the memory at the value and also bring that value into the cache. Then we flush the array from the CPU cache. We use this library function mmcl flush to flush that. This one eventually, there is an instruction called a cl flush to flush that. So then we flush all of those out of the cache. So they are guaranteed not in the cache anymore. Then we access the second page and the 8th page again. Okay. So what will happen after this is the 2nd page and 8th page will be brought back to the cache again. So this then after that we do a measurement. The measurement we use a special CPU feature called a real-time, some kind of real-time timer to do this. What we'll do is we are going to measure the time we spend on accessing each of those 10 bytes in those 10 different pages. First, we get the address of the first byte in the page. Then we just dereference that address. That's why we have a junk, because we don't care about the value there. The value will be, for those two, the value will be 200, but we don't care about the value. That's why good junk. So we measure the current time, then we measure the time again. So we get the time difference. Is this a code easy to understand?
Yeah.
Okay. Let me see if there are any questions here. Oops. Okay, let's just go to the demo. So I'm showing you, this is the same code. We used some library to use specific functions like this one, say flush, and also this function to measure time. So if we run this program, you can clearly see the difference. So see, those are the two we accessed, right? Index 2 and index 8. And you can see the time we spent to access the first byte in page 2 is only 26 CPU cycles. And the time we spend on number 8 is only 25 CPU cycles. But everything else is something 95 to 224 CPU cycles. You can say it's clearly those two are faster, right? That's because those two are already in the cache. Others are from the main memory. That's why they are faster. We can change this program to show you I'm not cheating here. So I just we can change this. What do you want to change? 7, 6, maybe add another one. Array 3. Okay, the value doesn't matter. We compile this again. We run this program again. And you can say, okay, this one is small, this one is 6. What are this one return? I forgot. So we access the 3, 6, and the 7, right? So see, this is 3, 25 CPU cycles, 6, 27, 7, 25. Everything else much slower, 100 something. You can run this multiple times and you always get a similar results. This one 24, 39, 39. Okay. Okay. Do you see the difference? Let me take a look at what CPU I have here. So I do a LS CPU. You can say I have an Intel CPU. I think we should be able to get the cache information here. Okay, it's not showing me cache information. But if we just search online, just Google this. Which website has all those information? I used to website. It shows all the information. How many cache lines? How many? Oh, this one is pretty good, I guess. Let's see, where's cache? This is number of cores here. Okay, here it says L1 cache size. So L1 cache, the CPU I'm doing the demo right now has 4 32K 8-way set associative cache just for the instruction. Then the data has a 12-way set associative cache. And the L2, we do not separate code and data anymore. So it's 8-way. Then level 3, I have a 8 megabyte cache. So the cache latency, I'm not sure what is this. Maybe this is CPU cycles. This is 5 cycle. This is 13 cycle. I'm not sure about that. Okay, does everything make sense so far?
Yes.
Okay, so as a homework today, you are going to run this piece of code on your own CPU and try to explain what happened there. Also, you will use the command ls CPU to find what CPU you are using, then just Google online to get the CPU spec. Okay, next we move on to the very interesting meltdown and spectral attacks. So how many of you heard of this before? No one heard of this? This was big in 3 years ago, I believe.
Yeah, I've heard about it.
Yeah, it's like the CPUs we manufactured in the last 20 years or even longer had this vulnerability, but no one knows about this. Okay. So we talk about Meltdown first. Meltdown is a hardware vulnerability affecting CPUs from the x86 families, IBM power processors, and also some ARM-based CPUs. And I believe luckily AMD CPUs are not affected by Meltdown and Spectral because they design a little bit different at that level. So Meltdown allows an attacker with long-privileged level process to read all memory locations, even if that is not authorized to do so. So a user application can use Meltdown to read other applications' memory content and also read the kernel's memory content. So Meltdown, there was a CVE number associated with it back in 2008, 2009. It was disclosed at the same time with Spectral, which is another bug. They are similar, but not the same. Spectral uses another feature about. So both Meltdown and the Spectral vulnerabilities were considered catastrophic by the security community when it was disclosed. Both of them, I think there were 2 papers on this. So some independent researchers, some researchers from Google and from some universities, they discovered this at the same time. They published a paper together, 2 papers together, one paper on Meltdown, on Spectrum. I believe one is published in Oakland, another one was published in Unix Security. So Meltdown use out of order instruction execution to leak data via a processor's covert channel. And the covert channel we're talking about here is cache. So it relies on 2 CPU optimizations. One is called out of order instruction execution. Then the second one is obviously cache. Cache is just to leak the data. Out of the order is the real problem. Execution is a real problem here. So we were talking about what is out of the order. So all of those attacks are kind of called the side channel attacks because the root cause is when you design a CPU, you try to make it faster. You come up with some optimizations based on some usage patterns, based on some heuristics that you try to make the CPU run faster. However, as long as the CPU runs faster, it also discloses some information like the cache, right? When you access data from the cache, it's faster, it's good, but also it discloses that what data the victim is using. So I believe there are more vulnerabilities like this at the CPU level. We just don't know. We do not know how to utilize, exploit them. We do not know what vulnerabilities are there yet. So let's explain a little bit of what is out of order execution. You probably studied this in your computer architecture class, I believe. The computer architecture class basically talk about how you design CPUs, right? So here we have a CPU with a 5-stage pipeline. We have fetch, decode, execution, read register, maybe. What is this? Read? I think it's read register. Then write back the result. So this is a 5-stage, FDERW. However, some of the stages, especially execution, it may take more than 1 CPU cycle. Let's say each block here means 1 CPU cycle. The fetch take 1, every fetch take 1 cycle, every decode takes 1 cycle, but execution depending on the instruction. Sometimes it take one cycle, sometimes it take multiple cycles, okay? The problem of this is you only have one execution unit. So if if we do a strict in order execution, means we will execute the instruction one by one. If we strictly do that, the problem is we can't get stuck at some instruction. That instruction will cost a lot of CPU cycles in execution. So when we get stuck there, other hardware modules in our CPU, like fetch and decode, they cannot work because everyone is blocked there. But their hardware, well, if they are not working at this CPU cycle, then are wasting its computing power, right? That's why people come up with out of order execution. So the CPUs we are using right now, they use out of order execution. So the idea is to move the dependent instructions. So some of the instructions, they are dependent on each other. Those instructions, you have to execute them sequentially because those results are dependent. But some of the instructions, they're not really dependent on the output of other instructions. So technically, you can execute some of them earlier than before, okay? So the idea of out of order execution is to move the dependent instructions out of the way of the independent instructions, rest the areas for dependent instructions. The benefit is you do not waste all the CPU units. Let's use this figure as an example. We have 5 instructions here. The first one is integer multiply. The integers in R1, R2, the results go back to R3. Then we have an add instruction to do R1, R3, the result go to R3. So obviously those two instructions are dependent with each other, right? You cannot execute the add instruction before the multiply instruction. That doesn't work. The third instruction is another addition instruction using R6, R7. So technically this one has nothing to do with the first 2 instructions. You can execute this one independent of the first 2. Then this one multiply is related, this one is also not related to the add one. This one is related to this one because this one uses R5 and the R5 has a value of generated from R6 and R8. So I don't remember what this figure is called. Anyone remember in your computer architecture class, what is this called?
Just pipeline diagram.
Oh yeah, pipeline diagram. Yeah, exactly. Yeah. So here what we have is the first line maps to the first instruction. 1 cycle for fetch, 1 cycle for decode. Then we have 4 cycles for execution, then read register and write register. So the second instruction, obviously, because the first one, when the first one is doing fetch, then we cannot do anything about the second instruction. However, when we are doing decoding of the first instruction, our fetch unit is not working on the first instruction anymore. That's why the fetch unit can work on the second instruction. Then we are doing the execution. Then we can use the decode unit, decode the second instruction. However, here, the execution unit is still working on the first instruction, so we cannot do anything. We have to wait. We wait 3 CPU cycles, then we start execution. However, the second instruction is simpler, so it only costs 1 CPU cycle to execute. Okay, so if you draw a pipeline figure like this, you will realize those 5 instructions we will take. So how many columns we have that means how many CPU cycles we are going to use, right? So this is a 1, 2, 3, 4, 5. This is probably 16 or 17 CPU cycles we need to execute those 5 instructions. If we strictly follow the order. However, what we can do is we can use out of order execution, and in out of order execution, we assume we have a multiple execution unit case. Okay, you can see here we only have one execution unit at any time point. Only one execution unit and only one fetch unit is using. However, in out of order, what we have is the first instruction is the same. The second instruction, what we do is we fetch, we decode, but we still have to wait here because the second instruction relies on the first instruction. The second instruction uses R3 as the input, and R3 is the output of the first one. So we have to wait here, okay? There's nothing we can optimize for this one. They have to be executed sequentially. However, the third instruction is AND R6, R7, and the result goes to R1. So we can fetch it, we can decode it, and we can execute by adding R6 and R7. So there is another execution unit. Then we read the register, but we cannot write it back because R1 will be used. R1 will be used in the second instruction. So we will wait until the second instruction is done. We will write it back. However, the execution is already done. It is temporarily stored inside the CPU. Then we do the same thing for the fourth instruction and the fifth instruction. Fifth instruction relies on the fourth instruction, so it has to wait. Okay, so you can see that in this out of order execution, the third instruction, technically, the third instruction, the fourth instruction finishes before the second instruction. That's why it's called out of order. The benefit of this is the whole thing will only cost 12 cycles. The previous one, it cost like 16 cycles. So this is a huge performance boost from 16 cycles to 12 cycles. That's 25% performance boost. So imagine how important this is for CPUs, especially you are competing with other companies, right? This is a huge boost. You do not need to add many other things. You need to add one execution unit here. You do not need to add a full core, just one execution unit and change the algorithm. Then your CPU get 25% boost. However, the problem is security. So in this, for Meltdown and the Spectrum, I will give you another virtual machine to work on. So there's a professor from Syracuse. He already developed several good labs to do Spectral and Meltdown. So what you need to do is I will give you the link. You download their virtual machine, then you read the document, and then follow the instruction. He gave a very specific instruction what you should do. Then you will run that and record what happens, even though they are in your virtual machines. So those code are actually physically executed on your CPU. So that's why it also has the same issues. However, some latest CPUs we are using, you can see here, this is a CPU I'm using, right? It says vulnerability Meltdown, not affected. Vulnerability is Spectral version 1, version 2, storage bypass, and there is a mitigation, okay? So depends on what CPU you have and also the configuration of your CPU, these labs may not work. But what you need to do is you just need to faithfully record if it works or not on your computer. It may not work. For some people it works, for some people it may not work. So let's take a look at the program here to try to understand what this attack is about. Let's see. So this is a kernel module. Okay, this is a kernel module. When it runs, runs inside the kernel, and the kernel module has a global variable called secret. It's just 8 bytes. Then this kernel module doesn't really. The kernel module doesn't really do anything. It will create a driver for you to interact with the kernel module. That's it. It will memory copy the secret to a secret buffer. Okay, so for 20 years, because of the memory isolation between kernel and user space, we think this secret is secure inside the kernel. However, use Meltdown, you will be able to steal this information from the kernel if your CPU hasn't patched this vulnerability. So I don't have a demo for this one. This is for your homework. Okay, let's move forward to another vulnerability called the Spectral. This Spectral is another optimization of the optimization is not called Spectral. The attack is called Spectral. The optimization is called Speculative Execution. So it's a feature of modern CPUs. It's quite similar to out-of-order execution, but it's a little bit different. So the difference here is out-of-order execution, we are talking about one sequence of instructions. You can see those instructions, there is no branch, okay? They are just one sequence. They are inside one basic block. Spectral execution is related to the branch instructions. It also optimizes when there are branch instructions. So basically, the processor can preserve its current register state and make a prediction as to what branch the program will follow, and speculatively execute the instruction along that path. So imagine there is a branch instruction, then there will be 2 passes. So when we do out-of-order execution, it will stop there because you don't know what branch you should execute. And the speculative execution, the CPU will do a guess. The CPU will guess, I should go to the left branch, I should go to the right branch, and do out-of-order execution on that branch. Okay, so if that branch eventually turns out to be correct, then the result of that speculative execution are committed, are saved, and that will yield a performance advantage over just waiting there, right? So even if that branch turns out to be incorrect, the CPU simply do not commit what has been calculated. So the CPU will waste some time and power executing that, but it will not make the program slower than it was supposed to be, right? So this is a feature on all modern CPUs. So some of the CPUs, modern CPUs, they can execute several hundreds of instructions ahead. Like I said, this is a CPU optimized. So work is done before it's known whether it is actually needed, so as to prevent a delay that would have to incur by doing the work after we know that it is needed. Here is one example. We have a C code here. This is an if statement. And this is if statement obviously generate two branches. So we have two variables, x and y. If x is smaller than a value, then we will execute the memory read operation here. We are reading some memory location to a global, to another variable. If it's not, then we just do not do this, right? So what we believe without this optimization, it works is every time we will compare x with this value, then we execute the instructions of the second statement. However, in fact, what the CPU does is before we do this compare, the CPU will make a guess based on history. For example, the last 5 times when we do this comparison, x is always smaller than this. Then CPU will go ahead to execute the instructions of the second statement. Okay. So how can this be a vulnerability? I mean, this is related to cache. So look at this specific code. If x is smaller than this, then we are going to read some data from memory to y. So this one is part of main memory. So when this happens, what we started in the cache side channel attack before is the data at this memory location will be brought to cache, right? So when this instruction is executed, the data is brought into cache and also this variable, okay? The problem, the vulnerability here is if the CPU finds out later this condition is not met, x is greater than this, it was then the CPU knows, oh, I'm not supposed to execute this several instructions like this. So I will not commit the result to the variable, which means the value of that memory location will not be brought into that variable. However, it will not clear the cache. The value is already brought to the cache, and the CPU will not clear that. That's the root cause of this problem. Since that data is brought to the cache and not cleared, then we can use cache side channel attack to get the value of the data in the cache instead. So those guys carefully designed some attacks based on this, and it will be used to steal things from kernel space as well. So this is called the first version, V1, version 1 of Spectrum. The version 2 of Spectrum is similar. It's the only difference is we're not talking about this kind of branch. We're talking about a branch to the kernel area, something like system call, those kind of branch. Does this make sense? This could be a little bit difficult to understand. Okay. So if we compare Spectrum and Meltdown, we would say Meltdown doesn't really use branch prediction. It only relies on out of order execution. And also Meltdown exploit a vulnerability specific to Intel and ARM processors, which allows certain speculative executing instructions to bypass memory protection. So that out of order execution, you can see the idea is very similar. So it's also one kind of a speculative execution. Meltdown access kernel memory from user space. It access causes a trap, but before the trap is issued, instruction follow the access, leaks the content of the data through a cache covert channel. So for Meltdown here, I don't have a Meltdown example code here. So this one only shows you the vulnerable program, but there are more Meltdown code to actually show you how to do that. So anyway, the professor from Spectral, from Syracuse, he has a very detailed instruction on those two attacks. So just follow those instructions. You should be able to do this as long as your CPU still have this vulnerability. Okay, so that's actually all the lecture part I have. Any questions? Since it's a holiday week, so this homework, I will give you more time. The due date will be next, we can do next Thursday for the due date instead of next Monday. So next Monday, we will have our last class and we're going back to software vulnerability. We're talking about heap-based buffer overflow for the last class. Then after that, we're going to have the final CTF. Okay, if there's no other questions, I guess we are done today. I will send you all the materials on Slack. Okay,
Thank you.
Okay, see you guys. Yes, the final exams, the written part will be take home. The CTF will be in class. Okay, see you guys next week.